Magnetic flux seems a little bit intimidating, but let's go ahead and try to define what that means. Let's say we had a circular area, and through that area there was a magnetic field. Well, that would be a very good symbol, good definition, and a good image to understand what flux is. So that's usually calculated by integrating the magnetic field over, well, dotting that really with this dA over here. And you could usually simplify that down a little bit and say that it would be just a regular B times the area times the number of links that it is coiled around. So like usually these things would be like, you know, coiled around or something, like a number of times. And because of the end there, I'm going to even put a little curly symbol here because we want to keep track of whether we have included the n in our calculation here or in our calculations later, because we're going to refer back to this flux. So I'm going to keep track of whether I've counted the number of links at that point or in other cases. So the straight line would be without the n, and the curly one would be with the n. Just so you can keep track of whether you've already counted the links or not. And of course, because of the dot there, because of the dotting, you're going to cosine of the angle between the normal. So like there could even be a little dot right there, because that would be the normal of that area pointing out, and you would basically get the B, whichever direction the B field is pointing. Usually it's going to be actually in the same direction as the cosine. So usually this stuff will go away, but basically that's how you want to think of this. So that's flux. And keep in mind that the units are going to be T, that's Tesla meters squared, which would be Webers. All right. Now, according to Maxwell's equations, changing the magnetic field will actually create an electric field. Now, an electric field is essentially a voltage difference, or we would say an EMF. So let's say that if we were to induce an EMF and create this EMF, that would be caused by the negative time derivative of this flux here. So it would be changing over time somehow, and that's essentially going to create that electric field, induced EMF. Well, let's take a look at some examples. Here I've got a coil, and there's a magnetic field going through it. And similarly, there's a current going in this direction, but right here, there's nothing happening. There's no change. And so, you know, if we were to calculate d over dt of I, for example, that would be equal to 0. That would create no EMF. If we were to look at the EI over here, that would be equal to 0. Over here, there is no change in the flux. So everything's equal to 0 here. This would usually happen either in the initial I, or it might happen at the very final I, so IF, the maximum I's. This is probably the most confusing thing I've ever said, but let's just say that we increase the magnetic field a bit here. What that's going to do is going to give us a induced EMF inside of this coil, which is going to give us a current inside the coil, which is going to then produce a magnetic field that's going to counter the growth. So essentially, we want the magnetic field to point this direction, the induced magnetic field, because this thing just grew, so we want to counter that with a growth over there. But in order to get that magnetic field to go that way, you have to create a current in this direction, right? So it would go into the page here like this, and it would come out of the page like that. So you're basically inducing that current by changing the magnetic field. Well, now let's try to look at it from the current's perspective, because how did we possibly increase that magnetic field in that direction? Well, we probably increased the current, right? So let's say we increase the current there. So now, in order to get the counter current, we're going to have to create an induced EMF over here. So what we're going to do is we're going to think of these inductors as batteries that are essentially along that circuit that are creating a voltage difference in the opposite direction. If the current is going this way and we're increasing the current in that direction, is we're going to want to create a current in the other direction, this way. That's going to be the induced current, and this will be the EI right here, and you'll get the minus on that side, the plus on that side, so the current is going that way. That's what the inductor's job is, to basically counter the growth of these currents, counter the growth of this magnetic field by creating magnetic field in the opposite direction, by creating a current in the opposite direction that's going to kind of counter the growth of, or to counter the change, because, well, apparently the universe doesn't like change. In the third example, we're going to be shrinking the magnetic field, and so of course that's going to create the current that's going to want to counter that change. So it'll create a current actually in this direction, because we shrunk it, so we want it back. We want that magnetic field back. So we're going to make that magnetic field in this direction, and in order to create the magnetic field in that direction, we had to create the current that was going in out of the page over here on the top in blue, and going into the page the bottom here, right? Perfect. So that would create the magnetic field in that direction. Now similarly over here, if we shrunk the current, because again, how do you shrink the magnetic field? Well, one great way to do that is to shrink the current. And so if we shrink the current, we're going to want to replace that current by creating the induced EMF that's going to put the positive on that side and the negative on that side, so that the current is going to go from that side that way, and here is the induced EMF. And so this is a great visual for seeing how the magnetic flux works and the induced EMF, the change of the magnetic flux, at least in terms of either a changing current or a changing magnetic field. But there are more ways that we can get this induced EMF. Now, some important equations that we need to know is the current. Like, how, if we were to calculate that, we would say I is going to be equal to the induced EMF divided by the resistance. There would usually be like a resistor along this loop somewhere, so you would put that in there. And you might actually want to calculate the I net, because obviously you're going to have two currents. So this one's in that direction, this one's in that direction. You know, these two are actually both in the same direction. But if you want to calculate the total net current, you'd need to say EI plus E from the battery, right? The EMF from the induced EMF and the EMF from the actual battery in that loop, the current divided by the resistance. So those are just some more equations that you might want to know. So recall that the induced EMF is caused by a change of flux. Now the flux has two components, the magnetic field, which we've already messed with here, and now the area, which we're going to try to change here. Got this rectangular loop, we're pulling it out of the magnetic field, and therefore we're losing magnetic field. We're shrinking the area, therefore we're losing the magnetic field that used to be there. Okay, now I want to do this in the right order, so I'm going to take step one is going to be changing the area. Step two is going to create the EMF inside of that rectangular area. So we got the induced EMF. And number three, it's going to create the current that's inside of there. Now the current is going to want to create the magnetic field that is essentially replacing what was lost. Okay, so we kind of want the current to go in this direction. So we'll put the current down, and that's going to be going in this direction, this way, and we want it to be going in that direction, because if it goes in that direction, then it will replace the magnetic field that we just lost. It's going to put that magnetic field right here, and that's the induced magnetic field. Okay, so it goes in that order. It's pretty important. A change of this stuff, it doesn't create a magnetic field. It creates the EMF, and that change of that EMF creates the current, which then creates the magnetic field. So it goes in that order. So we can actually explicitly state that the change of area is going to be equal to the change of flux. Put that right here. And we might also want to calculate the induced EMF, so we'll go ahead and do that. That's just going to be equal to B times the length times the velocity that we are pulling this out of. That's interesting. And if we want to calculate the current, that's equal to BLV divided by the resistance. Now one more thing. Let's remember magnetic force. So actually, if we have a current going in this direction and the magnetic field going in that direction, then we can cross those two things and we'll get a force going in this direction over here. So this is the induced force that was caused by this whole current being established. And Well, if we are pulling this thing this direction, we are going to need a force that direction as well. These two forces are going to be equal if we're going to want a constant velocity. So, you know, if we're trying to figure out what the magnitude of that force is, it's going to be b squared L squared V, and we're going to divide that by the resistance of the loop. And you might also want to calculate the power. So the power is going to be equal to F times the velocity. And so that's basically going to be another way to create the EMF. Now let's try to define inductance. Well, let's say we had our little circular area there, and we had an magnetic field going through that area. Now, I've already included the N in there, the number of links, so that's why we got the swiggly sign there. But we're going to divide that by the current that's going through that inductor right there, and that will give us the inductance. And I like to represent it as I, although it's usually represented as a capital L. I mean, it just makes a lot of sense to have it be I. But anyway, this is usually represented as Tesla meters squared divided by amps, which equals henries. And we may want to figure out the the induced EMF. We can actually replace, we could put an I there, and we could say the time derivative of the current. This is another way that we can sort of represent the induced EMF if we know the inductance and we know the change of the current over time. And there's most of the inductors are going to be solenoids, but if you are trying to calculate the inductance of a solenoid, you would use mu naught, and then you'd have the n squared, that's the number of loops, and the L, that's the length of the solenoid, and then there's going to be the area of the solenoid. So this is how you can calculate inductance. Now let's take a look at the RI circuits, which would be resistor or inductor circuits, also known as RL circuits. But it's going to have the battery, the resistor, and the inductor. And let's say we connected this switch over here. Now the inductor doesn't really like change, so at first it's going to have zero current going through it. And in fact, we can describe the rise of the current over time as saying I of t is equal to the EMF of the battery over there divided by the resistance. And then we got 1 minus e to the negative t over the time constants of inductance there. And I'll also solve this for t just for fun. So we could see at any point in time, you know, if you happen to know what the current is, you'll be able to figure out how long it took to get to that current. So E over here, it's not too bad. And yeah, so essentially it would take some time before this stuff reaches the full maximum current. And we could also describe the decay being I equals I naught, and then e to the negative t over t. And we'll describe the I max as being equal to EB divided by R. It's going to be at basically t equals infinity. And then the t, that's the time constant there, that's just going to be equal to the inductance divided by the resistance. So those are just some equations to know about this particular loop here. So now let's go ahead and try to set up a Kirchhoff loop inside of this circuit. We're going to go this direction along with the current. The current would be going that way. So at first we'll start off with the voltage of the battery, and then we're going to go with the current with the resistor, so we're going to subtract IR. And then the next section is the inductor. The way to represent that is just going to be the inductance times the time derivative of the current. And of course we'll set that equal to 0 in the end. Now there's some important things to just kind of remember about all this stuff. If you happen to have a longer wire, you'll have higher inductance. Now it may seem strange because if you look at this equation, you might say, oh, there's an L on the bottom here. How could it possibly be that if you increase the L, you should be getting smaller inductance? But at the same time, remember that this also is going to affect the area and the number of loops going around. So since you have the n squared and an area there, that's essentially going to destroy the L at the bottom over there. So if you have a longer wire, you're going to get a higher inductance. And if you have a low T, that's going to be the low time constant here, then you're going to get to the maximum current much faster, much quicker. And then also let's remember two very important cases for when the EMF is equal to 0. When the induced EMF equals 0, the inductor is going to be equal to, well, the inductor has 0 EMF going through it. That's going to be at I naught, and in the beginning, I naught, so the change is going to be equal to 0 at the very, very beginning, and at the very, very end, at the I max. So I max, the final charge state, there's going to be no more change in the current. And so therefore, at both of those situations, immediately before starting things at the very final end, there's no change in the current. But anytime there is no change in current, the EMF is equal to 0. So just keep that in mind. Let's also take a quick look at magnetic energy. Magnetic energy. So we'll call that UB being equal to 1/2 of the inductance times I squared. And we'll also say the magnetic energy density, which would be curly U. That's just essentially going to be UB divided by volume, right? But it would be better to say the magnetic field squared divided by 2 times mu naught. So a couple more important equations to remember. Now in mutual inductance, we have two coils that are so close together, like within millimeters, that the magnetic field of one coil is reaching across the coils of the other. And so therefore, if you change the current in one of them, it's actually going to create an induced EMF in the other coil. And so we have some equations to represent that. We'll say that the induced EMF in coil 1 is equal to the negative mutual inductance between the two, and then times the time derivative of the current 2. And we could also say that the EMF induced in coil 2 is equal to the negative mutual inductance times the time derivative of the current 1. And what is this mutual inductance that we speak of? It's going to be basically the flux, but this time let's try to track when we count those links, because we want the flux from coil 1, but we're going to count the links in coil 2, because remember that this is going across those coils, so we want that that magnetic field, and we want to count the coils in here. This is M2. So now we'll divide that by the current that's back in 1, and this is how we calculate the mutual inductance between those two. We could also do it the other way, so we could say we could take the second flux over here from 2, and we'll count the coils in 1, and then we'll divide that by I2. And this is how we can, another way we can get the mutual inductance. This is going to be the same exact number because it's the same thing. But that's essentially what mutual inductance is. So to wrap this up, let's recall the different ways that we can create an electric field. So one way is to just have regular old charges. We can calculate the voltage some distance away, KQ divided by R. But another way is to use the induced EMF. And recall that voltage is just E dotted with ds, right? So voltage equals voltage, that makes sense. Let's rewrite the EI in terms of the area, which I'll designate as the circular area, pi r squared, times the change of the magnetic field, d over dt of B. This is one way that we can get a change in flux. That makes sense. And that's just going to be equal to the electric field times 2 pi r. And that's going to be this type of thing. The electric field dotted with a circular circumference. So here this would be like an E loop circumference. And this one would be the B field, or the area of the B field. And if I was going to try to draw this a little bit, let's just say I had an area right here. And this would be my pi r squared. And inside of this area, I would have a B field, something like that, which is changing. And at some point, anywhere, I don't know, maybe even out here somewhere, I could figure out what the 2 pi r is, that a capital R. Those are two different radiuses. But you can see how essentially I could calculate the electric field over here by seeing that. And I mean, hopefully this visual makes a little bit of sense right here. And the last way that we can create the electric field is by using the motion. And so we'll have the third method down here, EI. It's again one of these induced EMFs, but this one was caused by motion. So that would be the BLV. And then you could also calculate the electric field by saying it's B times V. All right, so hopefully this was informative and helpful, and well, stay tuned for some more crazy physics.